You know, it's not long ago since I finished high school. I have many great memories. Socializing, competing, publishing, and presenting at international conferences. But all of which happened outside the classroom. I'm sure you all have great memories of your high school. Some of us might even remember our teachers. Reflecting back, I realized that teachers in Queensland needed to teach a certain curriculum in a certain way. There wasn't much room for maneuver, which in a way made everybody the same. So I guess it is fair to say that your typical classroom environment will consist of desks, whiteboards, a pre-programmed teacher, and a group of students robotically copying down word for word everything the teacher was narrating. There was only one way to put an end to this automated learning environment, and that was for someone to ask whether all was necessary for the exam. And that was the key to high school, knowing what you didn't need to know. I spent most of my high school learning about things I didn't need to know. For me, maths is a journey, and the most interesting journeys are the ones in which you explore and gain experience. So I believe maths should be taught as a journey, not a set of equations to be applied to something, as if maths is a set of dusty tools in the shed of science. For me, my maths journey started when I was really young. I've always loved numbers, and my parents realized that early on when I started doing even number addition at 3 years old. I also loved squaring numbers, and at one stage I could do 5-digit multiplication in my head. I actually had a book where I'd write down little tricks and formulae I'd use to solve such equations quicker. Pardon the writing, I was only 5 years old. So, yes, I love maths, and my various schools put me in competitions. At the age of 13, I was spotted by the National Director of the Australian Mathematical Trust, who put me in training for the Australian Olympiad team. And it was there that I discovered that I actually wasn't that good at geometry. I was, and still am, bad at drawing, and this made me scared of the subject. How could I possibly prove that 3 points line a line when my lines look like circles? So, I worked on geometry problems to maximize my chances of winning. And it was there that I discovered the unexpected beauty in geometry. Not in the drawing part, of course, but in the way certain mathematically challenging concepts could be explained simply through visualization. What is the infinite sum of a half, plus a quarter, plus an eighth, plus a 16th, etc.? While to some of you this sum may seem daunting, if you look at this animation where each time we're adding half the previous rectangle, it does make sense that these rectangles will eventually add up to a square that has area 1. But what if I now asked you whether parallel lines do meet? Well, parallel lines are defined not to meet. If you look at it in a certain angle, it does appear that these lines will eventually meet at a point at infinity. And it turns out this point is used extensively in mathematics nowadays. I was learning all this outside the classroom. Luckily, nowadays we have the internet where we can learn things in our own time. In fact, I didn't need school classes at all because participating in mathematical forums was like a class of its own. I was so involved in online communities that I actually started a blog where I post solutions to problems that I found beautiful, especially ones people couldn't solve. And it was there that I met Xuming Liang, who lives in America. At the time, we were both 16 and loved geometry and solving mathematical problems in general. Coincidentally, Xuming and I were both stuck on the same open problem, and it took us 5 days to solve this problem, a cycle. I'd work through the night, and Xuming would continue where I left off. Xuming would do the same, repeat. The time zone difference actually worked quite well. We had eyes on the problem for 120 hours straight. Now reflect on your high school experience where you had to solve 30 problems in 1.5 hours. Is it really testing our ability to think creatively? Unlike in high school, where you could submit your solutions and be marked, Xuming and I weren't even done. We stumbled upon a new theorem in mathematics, extending the one we had just solved. What our theorem stated was that a point in the triangle plane lies on isomorphically equivalent isopivotal cubics in its pedal triangles. But here's a diagram for the theorem. It's a bit simplified. Unfortunately, we too had no idea how to prove this problem, and it took us 6 months to finally figure out a way just to start the proof, and another week to solve it, let alone 9 months for it to be published. Who could have thought by the end of it that our diagram would look like this? What our theorem did was that it made the complex field of isopivotal cubics easier to deal with, and allows difficult geometrical problems to be solved by people with only high school level understanding of geometry. It avoids pages of calculation to more elegant and quicker approaches. In fact, when I tried to solve the equations of our theorem, my computer timed out. So clearly maths isn't just a set of equations, but more like a crime thriller where the build up to the ending is far more important than the ending itself. Xuming and I had to create new theory in the field of isopivotal cubics in order to solve our new theorem. And it turned out that these subsidiary results end up being the most important and widely applicable part of our article. Fermat's theorem is a perfect example of this. Back in the 1700s when it was formulated, people had no idea how to prove the simple-looking problem. But fast forward to the 20th century, where whole new fields of analytical number theory and algebraic number theory had to be invented in order to solve the problem. It was finally resolved by Andrew Wiles, but in contribution were hundreds of mathematicians worldwide. So just imagine learning the result. A to the x plus b to the x equals c to the x. What are you actually learning? The whole concept of thinking of mathematics as a journey follows from the idea that the ability to think creatively is far more important than the ability to know and to apply. In 2015, AlphaGo was placed in competition with Lee Sedol in the game Go. While the computer did win 4 out of 5 times, it was where the computer lost, which begs the question, how could a computer that could compute a surplus of 100 moves ahead lose to a mere human? And it was there that I realized that we have an edge over computers to visualize geometrically, to think abstractly and out of the box, and to use these qualities to create innovation. What this means is our human imagination and creativity cannot be replicated by a computer. So the question is, are we as the younger generation being given the best opportunities to use our talents and qualities in the best possible way? And currently, I don't believe our education system understands the importance of creativity. In schools, we're taught to set a follow of rules, procedures. We're taught to accept rather than question, to test rather than experiment. What is the point of 12 years of teaching if a simple computer program could do the exact same thing billions of times faster? We're being told that wrong is bad, and in the process, we're losing the fundamental property that makes us human: creativity. Just imagine a world where complex numbers didn't exist. And now imagine a poor inquisitive child asking his teacher, why are there solutions to x squared equals negative 1? We have solutions for x squared equals 1. 1, 4, 2, 9, 3, but why not negative numbers? And just imagine a response such as, just accept that there isn't. Or even worse, being ridiculed for claiming such numbers should exist, then the whole field of complex analysis and its ubiquitous applications in engineering wouldn't have been invented. We wouldn't be able to fly planes or even watch movies in our cinemas so comfortably today. So just imagine what kinds of innovations we might be losing nowadays. To encourage creativity, I believe we need to introduce real mathematics from an earlier age. That is, children need to understand the concept of logical thinking and proof writing earlier. For example, instead of homework being to repeatedly apply the same technique for 50 differently worded problems, why can't it be, think of this theorem or problem and how would you prove it? And then in the next class, discuss strategies of what the students saw and show them how the proof would work out. And instead of losing half of the students during class, I believe we need to incorporate methods of active learning where students will read content in advance and the teacher would go over what they do not understand. Lastly, I believe we need to make it clear that being wrong is okay. Because in my experience, I've learned the most out of being wrong. And knowing where I've gone wrong, coincidentally, has given me better understanding of mathematics as a whole. Similar ideas to what I've just been mentioning have been employed in Finland. And look where that's got them. They have the best education system in the world. They understand that our human imagination and creativity should be praised. It is more important to visualize than to know and to follow a procedure. Just like you cannot appreciate a story by reading its ending, you cannot appreciate maths, physics, art, or any subject by a set of rules and ways to apply them. We need to teach these subjects for what they are, a journey.